Hello, and welcome to the special PCEA series of lectures on PCB design. Our objective in this 12-part series is to cover the basic steps of designing a PCB. In this lecture, we are looking at libraries and components. Often when we think of a library, we would consider something like the Library of Congress, which has an interesting story behind it. When it was first purchased, that it was allocated $5,000 to purchase books for Congress to use, and it held a total of 740 books and 3 maps in the April of 1800. It now is one of the largest libraries in the entire world, containing 32 million cataloged books, other printed materials in 470 languages, and more than 61 million manuscripts. So this is often what we think of when we think of a library. This is very similar to the library that we'll be discussing here for your PCB design. Your PCB library holds the components that you will work with for your design. Now, in a previous lecture, we looked at the 4 steps of a PCB design, of being your library, your schematic, your printed circuit board, and then the documentation. In the library, we first want to look at what this library represents. Now, in the PCB design, as we see in the definition of process that we reviewed in another lecture, there are inputs and outputs in this process. And what happens is it creates what's called a parent and child relationship between each one of these stages. Each stage has a input and then an output. The only resource that is available to create your design is the library. The library represents something very unique to every company that is in the electronic industry. And that is, if there's an old saying, garbage in, garbage out. And when you begin a design with bad components from your library, it's going to result in lost time, lost money, also then wasted materials and everything else involved, not to mention the lost market share that you may have for a delay on releasing a product or something like this. So really, the way you want to look at your library is that it is a profit or a loss to your company. It is the resource and the resource that your designs will come from, and the quality of your library determines the quality of your PCB design. That's how serious this is. So why is this even a concern for us? Isn't the libraries handled by someone else? Well, there is a new trend in our industry, and it's been occurring for probably about the last decade now, is that more engineers are getting involved with the PCB design process. And with that, they now have the additional responsibility of creating their own components and handling that side of the design. There is a vast array of components. They come in every shape and size, package, or different things like that. So according to IHS Markit, there is over 1 billion different types of components available in the industry. So how do we handle such variety and design possibilities? Let's look at it this way. If I took a truckload of components and I dumped them in the middle of the gymnasium floor, and I said, okay, here, organize these. What's amazing about this, even though there is 1 billion components available, there's a uniqueness about them. And that is the fact that there are 5 pillars of your library. Now, I don't have time to go through each one of these in this presentation, but I do want to mention them. So number 1, there's singularity, managed, there's the architecture, review, and traceability. I do want to go into more detail on 2 of these. And the first one is singularity. The importance of having a single library. There's a principle in PCB design of having a single source of truth to work from. Nothing causes problems faster in a company than multiple libraries. This is what I refer to as the dreaded rogue libraries. And many times PCB designers or engineers will have their own personal library. Let me tell you that it is virtually impossible to manage that sort of structure in having multiple libraries. There's a short story I want to tell you regarding that. I was working for a company many years ago where when I first entered the company, they sat me down and they said, well, we have a 30% failure rate on our PCBs, not even getting through fabrication or assembly. And when I started investigating, and I found out that company was actually using 1,123 libraries, all different libraries, all different components in different states, and all this. And it was the result. We live in a world of cause and effect with PCB, and this was the effect. And the cause was the fact that we did not have a managed single source of truth to work from. And so the solution for that, and to get the company back on track, was I went in on a Friday evening, deleted all their libraries, and started over. So that was an interesting Monday morning when I came back in the office. And it was necessary, though, because we had to start over. We had to have a single source of truth. And this is the very first pillar, and probably the most important one. All the other pillars will fail because you don't have a single source of truth to work from. So the other thing I wanted to point out the other pillar I want to discuss just for a few minutes here is the architecture. Now, what's amazing about the fact that we have over 1 billion components available is that they all fall into 3 different areas. And this is category, families, and subfamilies. And if you look at many of the websites out there that handle components and such, they all have a structure to this. Now, I particularly use octopart.com, but this would be, for an example, their structure. So here you'll see in the red the category. So under the passive components, you then have the families. The families include capacitors, crystals, oscillators, EMI, RFI components, inductors, resistors, and transformers. Now, underneath those families, then you'll have subfamilies. Those will then be broken down into, for example, the type of capacitor and different things like this. This is a great way of organizing your library to be able to handle the various components that you'll see in your library itself, and understanding that everything has its place and a location for you to put it. Keep in mind, in the architecture of your library also, you want to have an area for models. This will be a place where you have a footprint and your symbols stored, and those will be used in various locations on various components. When I was going through school, one of the classes I dreaded each year was biology. And it was only because I knew we'd come to that time when we'd have to dissect the frog. And it was always difficult for me. But I did get through that. But one lesson I really learned from that experience was that every part in a frog has a function and a purpose. If you look at your library in the same way, each part, when you look at the anatomy of a component, each part has a function in your PCB design. So a component is broken down into 2 main parts, 2 areas. First off is your information side. Now, in the information side, you'll have your name, description. You'll have a parametric intelligent data that will be a part of that component. You'll also have sourcing or part choices that will be attached. Now, this is really interesting because with that sourcing, you can now have a basic component, and with its parameter information, then various sourcing then they can be added to it. which is really amazing because now you can then broaden your component availability, different things like this. The last item in that information side of a component is your data sheets. Now on the other side, you'll have your models. And this is consisting of your symbol, which is a graphical representation of electronic components used on the schematic. You then also have a footprint, also known as a LAN pattern. It's the arrangement of pads or through holes that connect a component to the printed circuit board itself. You then have a 3D model, which is a collection of vertices, edges, and faces that form a three-dimensional object. And then simulations. This is the use of a model to replicate the behavior of electronic devices. These two sides put together will create what's called an integrated component. And this becomes a very powerful item for you in your development of your product. Now, this chart actually shows a really interesting view of the library itself. If you look at this, you begin to understand that each one of these items on your part, your models, your parameters, your sourcing, your all that, all has its place and use in the design process. I'll give you an example. Your 3D model, it's for your PCB librarian, your designer, and then mechanical. Mechanical is concerned about your 3D model of how does your board fit into an enclosure, for example, different things like this. So look at these items as specific items that you need for your component. So let's look at specifically the schematic symbol. This is the first one that we're going to handle as we get in more into the other lectures. So the purpose of a schematic symbol is to assist with creating net lists or connections and assist humans reading the schematic. Now understand, and we'll talk more about schematics in our next module, but there are two types of schematic symbols. There is a simple component, which is we call the potato chip stuff. There's a resistor, capacitors, inductors, and so on. They're very simple, basic components. There's also then complex components, and a lot of times these are using multiple pins, rectangles, and different shapes, and different things like this. So looking at some best practices here of when you're creating a symbol for your library, is that first off, you want your inputs to be on the left and your outputs on the right. Now, this is a concept that we'll talk further about when we get into the schematic best practices, but it begins here in the library, which is a really important point here, is that your components are the basis of everything that you'll be creating in your PCB design. So also in the symbol, you'll have a pin properties, and we'll look at those more in here. But it's very important to keep your pins on a large grid. So there's a electrical hotspot that will become very important when we're connecting up our design. So this pin is probably the most important part of your schematic symbol. Here you have the pin name, you'll have a part number, and then you'll also have the hotspot on that pin, which will make the physical connection. So in our next lecture, we're going to be looking at the basics of the schematic.